Hello, this is Byron Washburn. I'd like to talk about conservation principles in the light of Lagrangian mechanics. So one thing we learned is that if we just look at the functional form of the Lagrangian, we can, just from looking at it, we can determine whether quantities like angular momentum or linear momentum are conserved. So this is a good point to step back and look at conservation principles, specifically conservation of energy, linear and angular momentum, in a much more sophisticated context. And so today what I'd like to talk about is the idea of what's called Noether's theorem and the relationships between conservation principles and symmetries in space and time. Okay, so this is conservation theorems revisited in the context of Lagrangian mechanics. So in the 1920s, there was a female mathematician by the name of Emmy Noether, and her primary work was in abstract algebra, but she came up with a very important theorem for physics, and which is today is called Noether's theorem. And basically, in summary, what Noether's theorem says is that symmetries lead to conserved quantities. This is really fundamental, okay? And you may ask yourself, why are certain quantities conserved and other quantities are not? For example, why is momentum conserved but not velocity or something like that? And so she answered this using a theorem, and basically what we can show is kind of what's summarized in this table as showing you behave is certain properties of space and time lead to properties of the Lagrangian, which eventually lead to conserved quantities. So that's summarized. So basically we have three conserved quantities that we're interested in: mechanical energy, linear momentum, and angular momentum. Okay, and according to Noether's theorem, a symmetry leads to each one of these conserved quantities. And this table here that I have here summarizes this. So I have some characteristic of my initial time, my inertial frame, the corresponding property of the Lagrangian, and eventually the conserved quantity. Okay, so what we're going to show in class is that something we're going to call time homogeneity, and that is a feature of time. And you may say, what does time homogeneity means? Well, one way of looking at it is, say I have a free particle, there's no net force acting on it, or no force at all acting on it. At say some time it's moving at a velocity v. And then I look at it at a later time, it should be moving with the same velocity, okay, as long as there's no forces on it. Now, say if the flow of time sped up or slowed down, then it would not be moving with the same velocity, okay. And so basically time homogeneity means that in some respects it's kind of loosely the rate that time is flowing at a given instant in time, all right. So time homogeneity, and our way of looking at time homogeneity, what it means is that if I do an experiment now and I do it at a later time, I will get the same results as long as I have the same conditions acting on this experiment. Okay. When time is homogeneous, the property of Lagrangian, there's no explicit function of time. There's no time. The Lagrangian may be an implicit function of time, but not an explicit function of time. And a conserved quantity is total mechanical energy. The second symmetry is space homogeneous. And what that means is if I say I do an experiment, and then I take the experiment, I just translate it in space. Okay, and then I do the same, I get the same results. Okay. In that case, the property of Lagrangian is that Lagrangian is invariant to translation, and the conserved quantity associated with that is linear momentum. And finally, the third symmetry is space isotropic. And what that means is, say I do an experiment, and then I just rotate the experiment in space without translating it. The property of the Lagrangian is invariant to rotation, and the conserved quantity is angular momentum. Okay, so that's the summary of the main result that we're going to do in class. And by the way, this is a table that you should know, because these concepts are transcendent and everywhere in physics. Okay, not just mechanics, but all branches of physics. Oh, sorry.
Hey, I know you good. Okay.
Okay, that was the janitor. Okay, so we're gonna move on here. Okay, a little entertainment for you. That was scary. Okay, so this is what we're gonna do in class here. Okay, so what are we actually gonna do in class? So basically, what I'm gonna do is I'm gonna look at the Lagrangian, and I'm gonna look at, for example, I'm gonna look at Lagrangian and show that when the Lagrangian is no explicit function of time, I'm going to get total energy conserved. So that's the first thing I'm going to show. The second thing I'm going to do is I'm going to take a Lagrangian, I'm going to translate it in space, okay, and show that the resulting Lagrangian results in conservation of linear momentum. And finally, the third thing I'm going to do in class is I'm going to take my Lagrangian, I'm going to rotate it in space, all right, and then show that the thing that's conserved when I do that is the angular momentum. Okay, that's what I'm going to do in class. All right. Okay. Now, I'm not going to derive those in class. I just talked about how I'm going to show those conservation principles. But let me talk a little bit more about that energy conservation first, and then in class I'll kind of talk through what we're going to do for angular momentum and linear momentum. But energy is really important, so I want to focus on that. So, let's think about my Lagrangian, okay? What I'm saying, if you go back to the energy principle, that said that, okay, energy is conserved, Lagrangian is not an explicit function of time. All right, what does that mean? That means that the Lagrangian is equal to, is a function of q and q dot, but not a function of time explicitly. Implicitly, it is a function of time because q and q dot are functions of time. So that implies that the partial of L respect to time is equal to 0. Okay. Now, what I'm going to do is I want to look at so that's what this result here. It means that the Lagrangian is not an explicit function of time. It's an implicit function of time. Now, what I'm going to show is I want to get a conserved quantity. Okay. And the way I'm going to get this conserved quantity, what I'm going to do is I'm going to look at the complete derivative of the Lagrangian respect to time. Now, when I do that, I have to use a chain rule. Remember, the Lagrangian is a function of q and q dot. So what I have to do is I have to do dl dq dq dt. So this is again the chain rule. Partial L respect to q dot dq dt, and then finally I have to do the partial of L respect to time. Okay, but that's 0 because I'm assuming that the Lagrangian is not an explicit function of time. Now, my next step is, one thing I can show is that a complete derivative of this, of my Lagrangian respect to q, is going to be equal to the same as the partial derivative because L is a explicit function of q, and the same thing for q dot is equal to the partial derivative of q dot. Okay, so then what I can do is I can say this is partial L respect to q, and then this thing is this q dot plus partial L respect to q dot, and then sorry, there should be a dot there, so that's q double dot, and then I have 0 because that's what I had there. Okay, now at this point here, what I'm going to do, okay, so I actually want to get that conserved quantity, okay, and because this is the quantity I'm going to get is going to be really, really important for when we talk about Hamiltonian mechanics. But so what I'm going to do here, right now what I'm going to do is I'm going to use the Euler-Lagrange equation. And the Euler-Lagrange equation says partial L respect to Q is equal to d dt of partial L respect to Q dot. I'm going to use, so what I'm going to do is I'm going to basically replace this term here with that guy there. And if I do that, okay, and what I'm trying to do is I'm trying to get a conserved quantity by doing this, okay. So then what I get is I get Q dot partial L Actually, sorry, that's a mistake. D dt. I can't forget. Oops. That's again. Okay. So what I have is here d dt. Okay, q dot. And then here I have here partial L q dot q double dot. Okay. Now, all that stuff there, I can rewrite as just one derivative of, so I have dl dt is equal to d dt of just one thing here. And I can write that thing as q dot partial L respect to q dot. And you can see that. You can see that, for example, if I use the chain rule here, d dt of q dot would give me q double dot times that, and then d dt of that would give me that right there. Okay, so that makes sense. Now, what I'm going to do here is I'm going to subtract the left-hand side, move it to the right-hand side, and then I can write this expression here as d dt of the Lagrangian, and that Lagrangian comes from, where does this L come from? That comes from this L here, minus q dot partial L respect to q dot equals 0. That's my main result. Okay. Now remember, how did I get this result? The way I got this result was I assumed that the Lagrangian was not an explicit function of time. This equation says that the rate of change of this thing here, this whatever that thing there, is equal to 0. So in the end, hopefully, well, obviously we want this thing here, this thing in the brackets, here. We want to show that's equal to a constant, and hopefully what that thing is equal to the total mechanical energy. That's what we want to show. Okay, now we're not there just yet. All right. Okay, so what I'm going to do is that thing, that quantity there, which is highlighted by the blue line, I'm going to set that equal to a constant. Now, I'm not going to set that equal to the total mechanical energy. You think, well, obviously this mechanical energy is why we conserve it yet. We're not just there just yet. So what I'm going to do is I'm going to define a new function. And I'm going to set that blue line equal to, I'm going to set this thing equal to something that's called minus a new function, which I'm going to call h, which is the Hamiltonian. If I do that, I can write a quantity called the Hamiltonian. Now, you say, why do I have the minus sign there? Well, in the end, this quantity here is actually minus the total mechanical energy. So I'm going to define something called a Hamiltonian. And a Hamiltonian looks like this. Q dot partial L respect to Q dot minus the Lagrangian. Okay, remember it's minus that quantity there. And that quantity there is called a Hamiltonian. Okay. Now, again, I haven't shown energy conservation just yet. Okay, so how I'm going to show energy conservation? Okay, how can I? I'm going to show that H is equal to the total mechanical energy system. So let's look at a conservative system. All right, and for a conservative system, what do we have? Well, we have a conservative potential energy. So for a conservative system, we say that U is a function of only a Cartesian coordinate x by itself. All right. That must mean that partial u respect to a generalized velocity is obviously equal to 0. There's no velocities there. Okay, and that implies that, well, u is just going to be a function of whatever my generalized coordinate q is. Okay. Now, from that we can say that from the Euler-Lagrange equation, or actually we can say partial L respect to q dot. Okay, now again, where does q dot, and Lagrangian is the kinetic minus potential energy. So partial L respect to q dot must be only equal to partial T respect to q dot. All right. Now, why am I calculating this guy here? The reason I'm calculating this guy here is because I want to put it in here. So let's look at the Hamiltonian. Hamiltonian is going to be equal to Q dot times the partial of L respect to Q. All right, let's just do that. Partial L respect to Q dot, but that's equal to partial T respect to Q dot minus the Lagrangian. Okay. And the Lagrangian is going to be equal to T minus U. All right. Now, now this gets there's a little tricky thing here. And what I want to do is, so I want to look at this term here. Okay, now how am I going to do that? Well, let me write it on the side. I'm going to show you something here. So say, instead of using Q, just to make things easier, say we say Q dot is actually V, okay, and then I have partial T respect to, instead of Q dot V. This is the same expression I have here. Let's look at that derivative. So that's equal to partial V of 1/2 mv squared. Okay. That's going to be equal to mv squared, but that equals to 2 divided by 1/2 mv squared. So that's equal to 2t. All right. So that must mean that this quantity here, instead of writing in terms of Q dot, I wrote in terms of V. That's going to be equal to, what do I have? I have now 2t minus t. I know, I'm sorry, put a u. Oh, come on. Oh, do better than that. Here we go. 2, okay, t minus t plus u. Well, that's equal to t plus u. And that's the total mechanical energy of the system. Okay. So that's really important. Now, it's a long way to get there. So what did I show? Well, basically what I did was I said Lagrangian is not an explicit function of time. That implies this. I looked at the rate of change of that using a chain rule, and I came up with a conserved quantity. This is this conserved quantity. I set that conserved quantity equal to minus h, and I defined a new function called the Hamiltonian. And then what I showed was that the Hamiltonian is equal to the total mechanical energy for a conservative potential. Okay. So this Hamiltonian is going to be a really important function. We're going to look at this Hamiltonian for a lot of different cases. In general, the Hamiltonian is not, for a very general case, you can always define a Hamiltonian. It may not be equal to the total mechanical energy for some systems, but for conservative systems, it will be equal to the total mechanical energy. Okay. Okay, so what did I just show? What I showed there explicitly is that if the Lagrangian is not an explicit function of time, the total mechanical energy is conserved. Now, what I'm also going to next show, and I'm not sure you're going to do this in class, is that if the Lagrangian is a invariant to translation, the linear momentum is conserved. And if the Lagrangian is invariant to rotation, then the angular momentum is conserved. How am I going to do that? So what I'm going to do is I'm going to look at so again, I'm just going to summarize what I'll do. If I look at linear momentum, when is linear momentum conserved? Okay, I'm going to look at, say I have some vector say I have for the alpha particle as a position vector r alpha. And then what I'm going to do is I have some coordinate system x, y, and z. And then what I'm going to do is I'm going to take that coordinate system and translate it in space, okay, by a little bit. That's a lot, but I'm going to do a little bit. And so what I'm going to really interested in is I'm going to look at, instead of r alpha, I want to look at how the Lagrangian changes if I go from r alpha to r alpha plus some translation in space. That translation doesn't have to be a little bit, but that's what we're going to do. So then, remember, my Lagrangian is going to be a function of, now in this case I'm going to say, just to keep things simple, x and x dot, okay? And so what I want to do is I want to look at changes in Lagrangian, okay, as I make that translation of the coordinate system, okay. And then we'll do this in class, but what I'll show is there's going to be some quantity that is going to be constant when I do that, and that quantity is going to be the momentum associated, the linear momentum associated with that Cartesian coordinate system. Now, what I'm going to do for angular momentum, to show that the concept of angular momentum, remember for angular momentum I say that space is isotropic. So what I'm going to do is I'm going to do a similar, I'm going to go from a position vector r to r plus delta r, except instead of translating this system, I just rotate the entire coordinate system. So r is this vector here. I rotate the entire coordinate system by a delta, delta theta, and then I have a new r. And then what I'm going to do is I'm going to look at changes in Lagrangian under that case where those changes are equal to 0. And from that, I'm going to get a conserved quantity, and that conserved quantity is going to be r cross p, or that is the angular momentum. Okay? So let's summarize here. So again, in class, we're going to talk about this idea, this concept of Noether's theorem, and that symmetries in space and time lead to conserved quantities. Okay? And we're going to show that basically if I can assume that time is homogeneous, the Lagrangian is not an explicit function of time, the quantity that's going to be conserved because of that symmetry is going to be energy. Okay. If space is homogeneous, meaning that if the system behaves the same, if I take and translate it in space, the Lagrangian is going to be invariant to translation, and the conserved quantity is linear momentum. And then finally what we'll show is that if I assume a symmetry of space being isotropic, as a result of that, the Lagrangian is invariant to rotations, the angular momentum is conserved. So this is pretty important stuff because this transcends mechanics. It's used in quite a bit in other areas of physics. And so we'll talk more about that in class. We'll see you there. Bye-bye.